In grade 10, you should have talked about motion in one dimension, right? And the equations that accompany that topic. We have Vf is equals to Vi plus A multiplied by the change in time, right? And another formula we have delta X is equals to Vf plus Vi divided by 2 multiplied by the change in time. And then Vf squared is equals to Vi squared plus 2A delta Y. Lastly, delta X is equals to Vi delta T plus a half A delta T squared. Instead of delta X, when you're talking about vertical projectile motion, we usually use delta Y, right? But the equations still work because vertical projectile motion is still motion in one dimension. So these are the equations we are going to mainly use to answer our questions under vertical projectile motion. In our first example, we have an object that is dropped from a height of 50 meters above the ground. Determine the time it takes for the object to reach the ground. Before we can even attempt answering our question, let's visualize. Let's see how our situation will look like. There we go. We have our object being dropped from a height of 50 meters. We have to use one of those four equations. But which equation are we going to use? That is going to be determined by the information we have. So what we need to do in this case is to jot down all the information we have. The information you have is what leads you to the equation you need to use. Let me show you what I'm talking about. When an object is dropped, it simply means that Vi is equals to 0 meters per second. If you drop an object, its initial velocity is 0. Okay, we will need to remember this at some point of time. Let's carry on. So we have delta Y. Delta Y can be equals to 50 meters or minus 50 meters, depending on which direction you take as positive. If you take up as positive and your object is going down, then the displacement is going to be negative. But if you take it down as positive and your object is going down, then your displacement is going to be positive. Unless the question states otherwise, I'm always going to take up as positive. So in this case, my displacement will be minus 50 meters. The object went down and I'm taking up as positive. So I have Vi, I have delta Y. Another variable I have is the acceleration. The acceleration is always 9.8 meters per second squared downwards. As I'm taking up as positive, then my acceleration will have a minus sign to show that it is going in the opposite direction. Minus 9.8 meters per second squared. What am I looking for? I'm looking for the time it takes to reach the ground. So these are the four variables I have. Which equation can I use when I have these four variables? Delta Y is equals to Vi multiplied by delta T plus a half acceleration delta T squared. Why am I saying so? I have delta Y minus 50 meters. I have the initial velocity, which is 0. Okay, I'm interested in the time, so that is my variable. I have the acceleration, obviously, which is 9.8 meters per second squared downwards. So on this equation, I have all the information I need except from the time, which I'm interested in. So I can go ahead and use this equation. That is how you choose a formula. You don't choose a formula first and then look for variables to substitute. No, it is the variables that lead you to the formula you need to use. So if we go ahead and substitute, the displacement or delta Y is minus 50 meters. So I'm going to have minus 50 being equals to Vi, the initial velocity, that is 0, like we've talked about, multiplied by the change in time. The change in time is our variable, it's what we're looking for. Plus a half, the acceleration is minus 9.8 multiplied by delta t squared. We're going to have minus 50 being equals to 0 multiplied by delta t. That will give us 0. 1 divided by 2 multiplied by minus 9.8 will give us minus 4.9 delta t squared. This is just going to be minus 50 being equals to minus 4.9 delta t squared. We need to divide both sides by minus 4.9. So let me just go ahead and do that. I get 10.2041 being equals to delta t squared. So the rounding off, before the final answer, you want to round off to 4 decimal places, okay? And then at the final answer, that is where you're gonna round off to 2 decimal places. And then now we can take square roots on both sides. If I do that, I get 3.19 seconds being equals to delta t. So it will take this object 3.19 seconds to strike the ground or to reach the ground. In this example, an object is thrown vertically upward with an initial velocity of 15 meters per second. Determine the time it takes for the object to reach its maximum height. Let's go ahead and have a sketch. Okay, so we have an object that is being thrown upwards with an initial velocity of 15 meters per second. So we have vi that is equals to 15 meters per second. We want to find the time it takes for the object to reach its maximum height. So delta t is what we're interested in, okay? But it is the time taken to reach maximum height. Like I've said previously, at the maximum height, v is equals to 0. So we have vf being equals to 0 meters per second, okay? That is always true at maximum height. At maximum height, the velocity is equals to 0. But the acceleration is and always is equals to 9.8 meters per second squared. So we have 9.8 meters per second squared. I'm sure you saw it in our previous example that it is important for us to choose a direction we want to take as positive. Either we take up as positive or down as positive. I'm going to take up as positive. So I'm taking up as positive. So from those 4 equations that we have under motion in 1 dimension, which equation can we use in this problem? Based on the variables we have, we can use Vf is equals to Vi plus a delta t. Let me explain why I'm choosing this formula. I have Vf at maximum height, which is equals to 0. I have Vi, which is equals to 15 meters per second. I have the acceleration, which is 9.8 meters per second squared downwards. And the time is what I'm interested in. So this formula works because it has the variables I have and I'm interested in. If I go ahead and substitute, Vf is equals to 0. So we don't have to worry about whether it is positive or negative because it is just 0. And then Vi, on the other hand, our object is thrown upwards. We are taking up as positive. So we must substitute that 15 meters per second with a positive sign. So we're going to have 15 plus the acceleration. The acceleration is always downwards. We're taking up as positive. So the acceleration should be minus 9.8. Delta t is what we're interested in. We'll take 15 to the left hand side. If we do that, we're going to get minus 15 being equals to minus 9.8 change in time. If I divide both sides by 9.8 minus 9.8, I have delta t. So let me go ahead and do that. So I'm dividing with minus 9.8 on both sides. If I do that, I'm going to have delta t being equals to 1.53 seconds. With time, we don't have to worry about direction. It is a scalar and not a vector. In this example, we have an object that is thrown vertically downwards with an initial velocity of 15 meters per second. After falling for 6 seconds, it is caught at a lower position. Determine the distance the object traveled during this time. Okay, let's make sense of our situation. So we have an object that is being thrown down at an initial velocity of 15 meters per second, right? And after 6 seconds, it is caught on its way down. What we're interested in is the displacement of the object from the time it is thrown downwards to the time it is caught 6 seconds later. Okay, so let's jot down the information we have. Which variables are we dealing with? Well, we have an initial velocity of 15 meters per second. Before we write all that down, let's decide on the direction. As always, let's take up as positive. If we do that, then we're going to have our initial velocity being equals to minus 15 meters per second. And then it is caught 6 seconds later. So we have our change in time, delta t is equals to 6 seconds. What else do we have? We are supposed to determine the distance traveled during that time. So we want delta y. That is what we're interested in. We have the acceleration. The acceleration is minus 9.8 meters per second squared. Of the 4 equations we have, which equation can we use to find delta y? It should be easy to see that we can use delta y is equals to vi multiplied by delta t plus a half a delta t squared. Why am I saying so? Delta y is what we're interested in. We have vi and we have the time and the acceleration also. So this is the right equation to use, okay? So let's go ahead and substitute. Delta y will be equals to vi, which is minus 15, multiplied by delta t, which is 6, right? Plus a half, the acceleration is minus 9.8. Delta t is 6, and we square that. So delta y will be equals to, now it's just a matter of putting that in your calculator, and it will be getting minus 266.4 meters. In this example, an object thrown vertically upward from a balcony with an initial velocity of 12 meters per second. It is caught at the same height. Determine the time it takes for the object to be caught. So let's make sense of this situation. We have an object that is being thrown up from a balcony to some maximum height, and then on its way down, it is caught at the same height it was thrown at. So its displacement is equals to 0 meters. Okay, we can deduce that. In order for us to be able to answer this question, there's 2 concepts I need to introduce you to. One concept is that the time it takes from an object to reach its maximum height is the same time it takes for the object to come from maximum height to the starting position. So what am I saying? If we calculate the time it takes to reach its maximum height and multiply that by 2, we would have the time it takes for the object to be caught, right? From the time it is thrown upwards. So that is one thing that is true and that we can utilize in order to answer this question. Another concept we can use is that if it is thrown upwards with a velocity x, when it goes down at the same position, it will have a velocity of minus x. So it's really up to you to choose which concept you want to use in order to answer this question. But let's go ahead and use both. So the first concept, I say that the time it takes to go from starting position to maximum height is the same amount of time it takes to go from maximum position or maximum height to the initial position it was thrown from. Let's jot down our variables and see if we can use this concept. So the initial velocity vi is equals to 12 meters per second. Why is it positive? We're taking up as positive like we always do. So that is where we are starting. Vi is equals to 12 meters per second. And then at the maximum height, we know that Vf is equals to 0 meters per second all the time at the maximum height. So we have Vi and we have Vf. Obviously, we have the acceleration. It is minus 9.8 meters per second squared. We're taking up as positive. That's why our acceleration is negative. The time is what we're interested in, delta t. So with these four variables, which equation can we use? Vf is equals to Vi plus a delta t. So let's take a look. Vf is 0, Vi is 12, plus the acceleration, which is minus 9.8 multiplied by delta t. If we take 12 to the left-hand side, we're going to have minus 12 being equals to minus 9.8 multiplied by the change in time. We need to divide both sides by minus 9.8. So let's just go ahead and do that. Delta t will be equals to 1.2245 seconds. We are rounding off to 4 decimal places because we are not at the final answer. We only round off to 2 decimal places when we are at the final answer. What more do we need to do? Well, not much. Delta t, or the entire time for the motion, is 1.2245 multiplied by 2, which will give you 2.45 seconds. This is the entire time taken for the ball to get thrown upwards and come back down to the initial position until it is caught. So this is one technique we can use. As I'm saying, we can also use the fact that if it is thrown up with a velocity of x at the same position as it is going down, the velocity will be minus x. We can also use this concept. So let's just go ahead and try it out and see if we're going to get the same answer. In this scenario, our Vi is still equals to 12 meters per second. What is changing is Vf. Vf is equals to minus 12 meters per second. The acceleration is the same as it always is, 9.8 meters per second squared. We're interested in delta t. Which equation can we use? The same equation we used previously. Vf is equals to Vi plus a delta t. Vf is minus 12 because when the object is going down, the velocity is going to be negative because we are taking up as positive. So we have minus 12 being equals to Vi. Vi is positive 12. So 12 plus the acceleration minus 9.8 multiplied by the change in time. We need to take 12 to the left-hand side. We're going to have minus 24 being equals to minus 9.8 multiplied by delta t. We're dividing both sides by minus 9.8 once more. And if you do that, you're going to get delta t being equals to 2.45 seconds. So as you can see, we end up with the same answer. So in this kind of situation, it's really up to you to decide on which concept you want to use. Let's talk about this special case. How do you deal with a problem where an object is dropped from a moving reference? For instance, a hot air balloon. How do you deal with a case where an object is being dropped from a hot air balloon, like in this case of ours? Well, when an object is dropped from a moving reference, a hot air balloon, for example, the initial velocity will be that of the reference. What does that mean? If you have a hot air balloon that is going up at a constant velocity of 5 meters per second and you drop an object, the initial velocity of that object is going to be that of the reference, of which in our case will be 5 meters per second. But then after dropping it, the acceleration of the object will be 9.8 meters per second squared, irregardless of that of the reference, right? Whether the reference was moving at a constant speed or it was accelerated, as soon as you drop it from the reference, it only takes its initial velocity. The acceleration will be 9.8 meters per second squared. Let's get right to the problem solving and cement the idea. So in this example, a hot air balloon ascends with a constant velocity of 5 meters per second. A ball is dropped from the hot air balloon at a height of 50 meters and falls vertically towards the ground. Determine the velocity of the ball when it reaches the ground. So let's take a look at the initial velocity, because with the moving reference, that is the first thing we should be tackling. So our object is being dropped from a hot air balloon that is ascending, that is going up at a constant velocity of 5 meters per second. So we have VI being equals to 5 meters per second. If you drop an object from a moving reference, its initial velocity is that of the reference. That is why we are saying that the initial velocity of the object is 5 meters per second. But its acceleration is not that of the reference. Its acceleration is and always is 9.8 meters per second squared. Okay? And then it is dropped from a height of 50 meters and is going towards the ground. So when it strikes the ground, its displacement will be 50 meters. Whether it's supposed to be plus 50 or minus 50, we'll take care of that later. Okay? And then what are we looking for? We want to determine the velocity of the ball when it reaches the ground. So that is VF. We want to find VF. With these 4 variables, which equation can we use? We need to use VF squared is equals to VI squared plus 2A delta Y. So VF squared will be equals to, we're taking up as positive. The hot air balloon is ascending, it is going up. So VI for the object is 5 meters per second upwards, okay? So we're gonna substitute that as 5. So we have 5 squared plus 2 multiplied by the acceleration. If we're taking up as positive, the acceleration will be negative. So we have minus 9.8. And then delta y, it is dropped from a height of 50 meters and is going down, right? We're interested at its velocity when it strikes the ground. So the displacement is minus 50 because we are taking up as positive. So we will have VF squared being equals to 1005. What we need to do now is to take square roots on both sides. If you do that, you're going to have 31.7 meters per second downwards. Velocity is a vector, so we always need to give the direction when we get our final answer. As you can see, this is quite an easy one. As soon as you sort out your initial velocity, we just stick to the basics. We write down our variables, we look for an equation, and it is direct substitution. But what if you're not dropping an object from a moving reference, but you're throwing it up or you're throwing it down? For instance, let's say we were not dropping the ball from the balloon, but we were throwing it up at the velocity of 10 meters per second. Then what would be its initial velocity? Will it be that of the balloon, 5 meters per second, that of which we are throwing it at 10 meters per second? Well, let's go ahead and find out. This is another scenario you might come across. A hot air balloon ascends with a constant velocity of 10 meters per second. A ball is dropped from the hot air balloon at a height of 100 meters and falls vertically towards the ground. Very similar to the last example, but let's hear how it differs. Determine the distance between the hot air balloon and the ball 2 seconds after the ball is dropped. Okay, let's conceptualize. Let's have a clear understanding of what is happening in our situation. Our hot air balloon is ascending, it is going upwards, and then a ball is dropped from the balloon. Okay, if the balloon is going up at a velocity of 10 meters per second, then when you drop a ball, it is going to have an initial velocity of 10 meters per second upwards, because if it is dropped, its initial velocity will be that of the reference. So we expect the ball to go up, reach maximum height, and start going down. This is what we expect to see. But what we want is the distance between the hot air balloon and the ball 2 seconds after it was dropped. So this is what we do in this type of situation. Our hot air balloon is still going up at a constant velocity of 10 meters per second. So we will find the displacement of the hot air balloon. After finding the displacement of the hot air balloon, we will find the displacement of the ball. And then with those two values, we're going to be able to find the distance between the ball and the hot air balloon. Let's go ahead and start with the displacement of the balloon. So for the balloon, it is moving at a constant velocity. So our acceleration is equals to 0. And its velocity is 10 meters per second. It's not changing whatsoever. We have the time, which is 2 seconds, and we're interested in the displacement. The equation we need to use with these variables is delta y is equals to vi delta t plus a half acceleration delta t squared. So delta y will be equals to the initial velocity of the hot air balloon, that is 10 meters per second, multiplied by 2, which is the time, plus a half, the acceleration is 0, multiplied by 2 squared. So delta y will be equals to 20 meters. After 2 seconds, the hot air balloon has covered 20 meters. That is the displacement of the hot air balloon. Let's now go ahead and take a look at the displacement of the ball. Its acceleration is and always is 9.8. Its initial velocity will be that of the hot air balloon, 10 meters per second. The time is 2 seconds, and we want to find the displacement. We are going to use this same equation, of which if we substitute, we have delta y being equals to vi is 10, delta t is 2, plus a half, the acceleration is minus 9.8 multiplied by 2 squared. The displacement of the ball is 0.4 meters. We're taking up as positive, okay? So this is the displacement of the hot air balloon, and this is the displacement of the ball. They started at the same position. 2 seconds later, the displacement of the hot air balloon is 20 meters, while that of the ball is 0.4 meters. We're interested in the distance between the two, which will be 20 minus 0.4. The distance is going to be equals to 20 minus 0.4, which is equals to 19.6 meters. Well, in the previous problems we have been solving, a ball is always dropped from a hot air balloon. But that is not always the case. Sometimes it is thrown while it is on a moving hot air balloon. In that case, the velocity of the ball, the initial velocity, is no longer just that of the hot air balloon. It is actually a combination of that of the balloon and that which you're exacting on the ball. Let me show you what I'm talking about. A hot air balloon ascends with a constant velocity of 5 meters per second. A ball is thrown downwards with a velocity of 3 meters per second from the hot air balloon at a height of 50 meters. Determine the velocity of the ball 3 seconds after it is thrown downwards. Let's concentrate on the initial velocity of the ball before we worry about everything else. So the initial velocity of the ball will be that of the balloon plus that at which it is projected at. But we need to pay close attention to the direction. The balloon is going up. So if we take up as positive, then the velocity of the balloon will be 5 plus the velocity at which it is projected. It is projected at 3 meters per second downwards. So if up is positive, down will be negative. So we have 5 plus minus 3, which will give us 2 meters per second. So this is actually the initial velocity of the ball. This is the approach we take all the time when you have a moving reference and you project a ball at a certain speed x. It will be that of the reference plus that at which you project your object at, okay? But paying attention to the direction. It is not that complicated. You just add in the two velocities while respecting that velocity is a vector, not forgetting the direction. Well, we have the initial velocity of the ball. We want to determine its velocity 3 seconds after it is thrown downwards. Let's take a look at the other information we have. The acceleration, obviously, 9.8 meters per second squared. We have the time, delta t, which is equals to 3 seconds. We are interested in the velocity, so we want Vf. With these four variables, it's quite easy. We have Vf being equals to Vi plus a delta t. Vf will be equals to, what is Vi? The initial velocity is 2 meters per second plus the acceleration, which will be minus 9.8 if we are taking up as positive. The time, the scalar, always positive, so we multiply that by 3. Minus 27.4 meters per second. Well, this is just 27.4 meters per second downwards. That negative sign tells us that it is downwards because we're taking up as positive. So just like that, we have solved the problem. It's not that complicated. Just a tiny adjustment and we have figured it out. If you were multitasking, this is probably a good time to stop because we have a scenario involving two balls. So let's take a look and see what is happening. A ball is dropped from a height of 20 meters. At the same time, another ball is thrown vertically upward from the ground with an initial velocity of 15 meters per second. Determine the time it takes for the two balls to meet. Let's take a look at the sketch. So we have the ball that is being dropped. Let's call that ball A, okay? And then we have the other ball that is being thrown up at an initial velocity of 15 meters per second. Obviously, they're going to meet somewhere in the middle. What we want is the change in time, is the time it takes for the two balls to meet. Let me show you how we tackle this type of problems. So let's say that A and B, they meet at this point, okay? This is the displacement for ball B, and this is the displacement for ball A. The only thing you need to realize now is that if they meet when A has traveled a distance x, then the distance that B will have traveled is 20 minus x, because they are 20 meters apart from each other. This is the only thing you need to realize. As soon as you make sense of this question becomes extremely simple. So let's go ahead and see how everything else will look like. Let's pay our attention to A first. So for A, we have delta y, which is equals to x. It is being dropped, so Vi is equals to 0. The acceleration is 9.8 meters per second squared. What else do we have? We are interested in the time. The equation that we're going to use, we're going to say that delta y is equals to Vi delta t plus a half acceleration delta t squared. So delta y is x meters, right? If we take up as positive, then that should be minus x being equals to vi multiplied by delta t. Vi is 0 multiplied by delta t plus a half. The acceleration is minus 9.8 delta t squared. Minus x will be equals to 0 multiplied by delta t, that will be 0. And then a half multiplied by minus 9.8, that is minus 4.9 delta t squared. We have two variables, x and delta t. So let's call this equation 1 and use ball B to find equation 2. Let me just get rid of this. For ball B, we're going to have delta y being equals to vi delta t plus a half acceleration delta t squared. The displacement of ball B, we've already deduced that it should be 20 minus x. So 20 minus x will be equals to its initial velocity, which is 15 meters per second, multiplied by delta t, plus a half. The acceleration is minus 9.8 delta t squared. So 20 minus x is equals to 15 multiplied by delta t, minus 4.9 delta t squared. So if we make minus x the subject of the formula, we're going to have minus x being equals to 15 multiplied by the change in time, minus 4.9 delta t squared minus 20, equation 2. We can go ahead and equate these two equations, right? If we do that, we're going to have minus 4.9 delta t squared being equals to 15 delta t minus 4.9 delta t squared minus 20. If we take minus 4.9 delta t squared to the left hand side, we're going to have minus 4.9 delta t squared plus 4.9 delta t squared, which will give us 0. So we have 0 being equals to 15 delta t minus 20. Minus 15t to the left hand side, minus 15 delta t is equals to minus 20. If we go ahead and divide both sides by 15, we get 1.33 seconds. That is the time it takes for the two balls to meet. Let's see if it really makes sense. Let's substitute delta t into equation 1, okay? We're going to have minus x being equals to minus 4.9 multiplied by 1.33 squared. So minus x is equals to minus 8.67. So x is equals to 8.67 meters. And 20 minus x will be equals to 11.33 meters, which makes sense. But what if the balls are not thrown at the same time? What if one between the two balls is thrown a second later? How do we deal with such a problem? This example is very similar to the one we did before. The only difference is that the second ball is projected 1 second later. Let's go ahead and take a look and see what is happening. So a ball is dropped from a height of 20 meters. 1 second later, another ball is thrown vertically upward from the ground with an initial velocity of 15 meters per second. Determine the time it takes for the two balls to meet. So we can say that this is ball A and this is ball B. So let's go ahead and concentrate on ball A before we can move to ball B. So for ball A, we have the initial velocity. It is dropped. So we have VI is equals to 0. We have the acceleration, obviously, 9.8. What else do we have? Do we have the time? No, we don't have the time. but we have the displacement. We can take the displacement of ball A as a variable k. If we take up as positive, we must substitute k with a negative sign. So the displacement is equals to k. I think that is all we need to see that we can use our equation delta y is equals to vi delta t plus a half acceleration delta t squared. The displacement will be minus k meters because we are taking up as positive. So everything going down should have a negative sign. So minus k is equals to vi, which is 0 multiplied by delta t, plus a half. The acceleration is minus 9.8 t squared. So let's just use t squared instead of delta t. We're going to have minus k being equals to minus 4.9 t squared. We have two variables, k and t. We call this equation 1. And then we can use ball B to find equation 2. We are going to use the same equation for ball B, but we must remember that delta y, the displacement for ball B, is 20 minus k. If we remember that, then we should be good to go. So let me go ahead and erase that and carry on with the problem. This is for ball A, and then for ball B, substituting into the same equation, we're going to have 20 minus k being equals to 15 multiplied by delta t. But ball B was projected 1 second later. So if for A, we're saying that the time is t, for ball B, the time should be t minus 1 because it is projected 1 second later. If it was projected 2 seconds later, it will be t minus 2. So that is how you sort of account for the time being 1 second later. Okay, so t minus 1 plus a half, the acceleration minus 9.8 t minus 1 squared. So 20 minus k will be equals to 15 multiplied by t, that is 15t, minus 15, right? 15 multiplied by minus 1. And then a half multiplied by minus 9.8, that will be minus 4.9. And then t minus 1 squared, that is t squared minus 2t plus 1. So 20 minus k is equals to 15t minus 15 minus 4.9 t squared plus 9.8t minus 4.9. So minus k will be equals to 15t plus 9.8t minus 15 minus 4.9 minus 20. We're taking this from the left hand side to the right hand side. And lastly, minus 4.9 t squared. Minus k will be equals to, what is 15t plus 9.8t? That will give us 24.8t. Minus 15 minus 4.9 minus 20 will give us minus 39.9. And lastly, minus 4.9 t squared. This is equation 2. Now we can go ahead and equate equation 1 and 2. If we do that, we're going to have minus 4.9 t squared being equals to 24.8 t minus 39.9 minus 4.9 t squared. Obviously, minus 4.9 t squared and minus 4.9 t squared will cancel out when you take either to one side. So we're going to have 24.8 t minus 39.9 being equals to 0. So 24.8 t is equals to 39.9. If we divide both sides by 24.8, so let me just go ahead and do that. We're going to have 1.61 seconds.